Welcome back. Today we're going to be looking at topic 5.5, and this topic is looking at solving problems using tables and diagrams. So mathematically, I'm not going to be showing you much different today, but I am going to show you some strategies to use tree diagrams and charts or tables to solve some of our probability problems. Now, before we get into the examples, I just want to look at some vocabulary here. So I'm just going to cover up the examples for now and looking at some of our vocabulary. First of all, if we're looking at odds, remember that odds and probability are different. Odds are part to part, and probability is parts to whole. And so if we're looking at odds in favor of, we would have what we want on the left-hand side and what we don't want on the right-hand side. So in other words, we're looking at for and against. And if it's odds against, we're looking at against to for, or against and then in favor of. Now for probability, probability is parts over whole, so it's what we want over the total. Now, if two events are mutually exclusive, we're talking about or. Mutually exclusive means that there is no overlap if we were to create a Venn diagram. So nothing in common. So probability of A or B would be the probability of A plus the probability of B. If two events are not mutually exclusive, that means if I draw a Venn diagram, there is some type of overlap. So the probability of A or B is the probability of A plus the probability of B minus the overlap. So the probability of A and B. Now, if we were talking about independent and dependent events, we're looking at and situations. And so if something is independent, that means that one outcome does not rely on the other. So if we were talking about cards, it would be with replacement. And for dependent, one outcome impacts the other. So we would be talking about, for example, with cards, something without replacement. So independent, we might be looking at rolling a die and tossing a coin. With dependent, we might be looking at cards where one card is pulled out, kept out of the deck, and not put back in. Or a bag of marbles where we pull out a marble and we don't replace the marble before we pull out the next marble. All right, so we're going to be using these formulas throughout this lesson, and feel free to refer to your formula sheet at any point in time. And again, as always, when we're going through the examples, feel free to pause the video, try them on your own, and then take a look at the answers. All right, so this first example, it says that the table shows how the students in a large high school generally travel to school. And the first thing we're asked to do is just to complete the totals in the chart. And so if I add these all up here, 350 plus 100 plus 75, I'm going to have 625. 300 plus 175 plus 100 is 575. The amount of people taking a bus is 650. A car is 375. Other is 175. And the total amount of people in the school is 1,200 students. So the first question actually says, how many students attend the high school? Well, that's 1,200 students. Now let's look at some probabilities here. So it says, use the numbers in the table to determine the probability of M. Well, the probability of M, that's the probability of someone being male. Well, if we look at our chart here, there are 625 males. So 625 males out of 1,200 students. And if we reduce that, that gives us 25 over 48. Now the next one is presented as a conditional probability. So this is the probability that someone's driving a car given that they're male. And if you remember from our last lesson, the probability of the car given the male part will be our denominator. So we have to consider how many males we have, and that's 625. And out of those 625 people, oh, I have a typo here. This is actually supposed to be a 2. Out of the 625, 200 people drive a car. So again, there's just a typo there. I think it's correct in your notes, however. So 200 people out of 625 drive a car given that they're male. So that reduces to 8 over 25. Now, the probability of M given C. Well, this is the probability that someone is male given that they drive a car. So we start off by looking at how many people drive a car, and that's 375. And out of those 375, 200 of them are male. And so that reduces to 8 over 15. So again, notice that our male here becomes our denominator. The car here becomes our denominator. Now, what about the probability of being male and driving a car? Well, how many males also drive cars? Well, if we take a look there, the number of males that also drive a car is 200, but now we're looking out of the total possible. So 200 males out of 1,200. So the probability of males and driving a car is 200 out of 1,200, which is 1 over 6. All right, let's consider some other probabilities from this chart here. So what is the probability that a student selected at random is female? Well, there are 575 females out of 1,200 students, which is 23 out of 48. And what's the probability that someone travels by bus? Well, traveling by bus, we have 650 people traveling by bus out of 1,200. So 650 out of 1,200 reduces to 13 out of 24. So what's the probability that someone is female and travels by bus? So is female and travels by bus. So that's going to be 300 out of the 1,200. So this is 300 students out of 1,200, which gives me 1/4. Now, this conditional probability is often the one that some people will struggle with, so you might want to put a huge star by it right here. So the question says to identify the following events and determine the probability that a female student travels by bus. Well, the part that we know for sure is that the student is female, and from there we want to know how many people travel by bus. So we're actually looking at what's the probability that someone travels by bus given that they're female. So notice that it's written female student travels by bus, and then they're reversed here, and that's because we're first told it's a female student. We know it's a female student, and from there, how many of those females drive a bus or take a bus. So it's the probability of someone taking a bus given that they're female. So this is going to be 300 out of 575, which is 12 over 23. Now for the second one, it says, what's the probability that a student who drives to school is male? Well, we know that the student is driving to school. We want to know how many of those driving to school are also male. So we're actually looking at the probability that a student is male given that they drive to school. And so there are 375 students who take their car to school, and there are 200 students out of those that are male. So that reduces to 8 over 15. The last question for this example, it says, are the events the student is female and the student travels by bus independent events? Well, if we check here, independent events means that the probability of A and B has to equal the probability of A times the probability of B. So let's take a look at what we know. We know that the probability of F and B, so being female and riding the bus, is 1/4. So we had that from up here. Okay. And now we want to see what is the probability of F times the probability of B. Well, the probability of F, or the probability of being female, we have that again from before, is 23 out of 48, times the probability of someone taking the bus is 13 out of 24. And if we multiply that out, we're going to get 299 over 1152. These are not the same. And since they're not the same, it does not meet the criteria for independent. So these are not equal. So not independent. In other words, they're dependent. All right, so we're going to be looking at 5 examples today. We've just finished the first one. As we go through each of these, I'm trying to show you the different varieties that you can see. Some of these questions relate directly to questions on your unit review, so you may want to refer back to these notes a few times. All right, example number 2, we're going to take a look at a tree diagram. And just like any of the questions that we've done before, setting up all of our probabilities before we build our diagram is going to be helpful. So here's the question. It says students were given the following problem to solve. The odds, notice it says odds, the odds that Ava will pass her math this semester is 4 to 1 in favor. So 4 to 1 in favor. And the odds that she will pass English this semester are 1 to 9 against. Now, we're told that these events are independent. So in other words, passing math has no impact on her passing English. So if these events are independent, determine the probability to the nearest hundredth that she will pass math and English, math and not English, and math or English. Sorry. All right. Now it says to start off by expressing the odds in probabilities, and that's always a good place to start. So we know that the odds of passing math are 4 to 1 in favor. So the probability of passing math in favor of means 4. And remember, probability is parts to whole. 4 plus 1 is 5. So the probability of passing math is 4 over 5, meaning that the probability of not passing math is 1 out of 5. Now the probability of passing English, it says the odds that she will pass English this semester are 1 to 9 against. So that means in favor of is actually 9, and 9 plus 1 is 10. So the probability of passing English is 9 over 10, meaning the probability of not passing English is 1 over 10. Now, part B says some of the students chose to use probability formulas to solve this problem, and we're going to show the method below. So the first question here, we're looking at the probability of passing math and English. So probability of passing math and English is going to be the probability of passing math times the probability of passing English, because we're told these are independent. So the probability of passing math is 4 over 5. The probability of passing English is 9 over 10. And if we multiply that out, we get 36 over 50, which reduces to 18 out of 25. Now, what about the probability of passing math and not English? Well, this is going to be the probability of passing math times the probability of not passing English. So the probability of passing math, again, is 4/5. The probability of not passing English is 1 over 10. So this gives us 4 over 50, which is 2 over 25. Now the last example, it says passing math or English. So now we're looking at something that's either mutually exclusive or not mutually exclusive. Since we have a value for the probability of M and E, we know that this is not mutually exclusive. So it's going to be the probability of M plus the probability of E minus the overlap. So minus the probability of M and E. Now, if we didn't know if there was an overlap, we would have to probably do a little bit more work. But we're told right off the bat here that there is a value for the probability of M and E, and so we're going to use that for this question here. So the probability of M is 4 over 5, plus the probability of passing English is 9 over 10, minus our overlap, which we've calculated before, is 18 over 25, equals 49 over 50. So pretty good shot that they're going to pass one or the other or both. Now, formulas is one way to go. Another way that lots of students will use is tree diagrams. Now, with the tree diagram, we set up our events. The event is happening or not happening, and then we branch out from there, and in between, we're listing our probabilities. So our first event is math. We either pass math or we don't pass math. Well, we're told we have a 4 out of 5 shot of passing math, which is 0.8. I'm going to use decimals because unless they're messy numbers, decimals are much easier and much more visual to work with. So 4 over 5 is 0.8. And so if we have a 0.8 chance of passing, that means we have a 0.2 or 1 out of 5 chance of not passing. Now, if we pass English or pass math, then we're either going to pass English or not pass English. We know there's a 90% chance of passing English, meaning there's a 10% chance of not passing English. If we fail math, the probability of passing English is still 0.9, and the probability of not passing English is 0.1. So from there, we rated our scenarios. The first one is the probability of passing math and passing English. And then we have the probability of math and failing English, the probability of not passing math and passing English, and then the probability of not passing math and not passing English. Using the tree diagram helps us to guarantee that we get all of our possibilities listed out. So the probability of passing math and failing English is 0.8 times 0.1, which is 0.08. For the next one here, we've got 0.2 times 0.9, which is 0.18. And the last one here, we've got 0.2 times 0.1, which is 0.02. Now, if we add these up, 0.72 plus 0.08 plus 0.18 plus 0.02, we should get a total of 1. So our first probability that we were looking at was the probability of passing math or English. Well, if we look on our chart there, that gives us 0.72. For the next question, we were looking at the probability of passing math and not passing English. Well, that's on our chart already, is 0.08. And the last question was asking us the probability of passing math or English. So the probability of passing math or English. Well, if we look those up, all of the places where we pass math or English would be here, or here, or here. So we're adding all of those up. 0.72 plus 0.08 plus 0.18 gives us 0.98. Now, another way that we could do that question is to just take the 1 and subtract 0.02, which would also give us 0.98. All right, so let's take a look at another tree diagram question. This may be a time where you want to choose to pause the video, try the question, and then come on back, but we're going to work through it here right away. So example number 3 says, in a game of field hockey, the probability that the Dinos score a goal from any short corner is 1/8. During the first half of a match, they are awarded 2 penalty corners. And we're going to use the probability to determine that there's 2 goals, 1 goal, at least 1 goal, or no goals. So we're looking at 2 different goals here. And so setting up our chart here, we have getting the goal or not getting the goal. And just because I'm going to be using G twice here, I'm going to use a G1. So goal 1, and then we'll use goal 2. So we either make goal 1 or we don't make goal 1. And then we either make goal 2 or don't make goal 2. And then make goal 2 or don't make goal 2. If we're looking at our probabilities here, the probability of getting a goal, so the probability of making a goal is 0.8. The probability of not making a goal then, or sorry, not 0.8. Sorry, it says 1/8. So the probability of making a goal is 1/8. So that means the probability of not making a goal is 7 out of 8. Now these are independent events, so the probability of making goal 2 is also 1 out of 8. Not making it then is 7 out of 8. Making it is 1 out of 8, and not making it is 7 out of 8. So we read out our scenarios. The first one is the problem of making, or the probability that we make goal 1 and goal 2. Then we've got the probability of not making, or sorry, making goal 1 and not making goal 2. We've got the probability of not making goal 1, but we do make goal 2, or the probability that we miss both of them. So not making goal 1 and not making goal 2. So if we write out our scenarios here, we would have 1/8 times 1/8, which is 1/64. For making a goal and missing a goal, we'd have 1/8 times 7/8, which is 7 out of 64. Missing and making would be 7 out of 8 times 1 out of 8, which is also 7/64. And the last example, missing both, 7/8 times 7/8, which equals 49 over 64. And again, if you add these up, everything should add up to 1. So let's take a look at our actual probabilities here. So probability number 1, it was asking us for the probability of making 2 goals. So the probability of making 2 goals was the probability of goal 1 and goal 2. That's going to be 1 over 64. The next one says the probability of making just 1 goal. So that means we either get a goal and miss a goal, or we miss a goal and get a goal. So this one's going to be 7 over 64 plus 7 over 64, which equals 14 over 64, and reduced, that would be 7 over 32. Part C asks us to get at least 1 goal. So that means we either get both goals, or 1 goal, or 1 goal. So adding those all up, or again going 1 minus 49 over 64, adding those all up, we would get 15 over 64. So we're going to go 1 over 64 plus 7 over 64 plus 7 over 64 equals 15 over 64. Or again, you could do your complement. 1 minus 49 over 64 equals 15 over 64. And our final example here, we're asked for no goals. Well, missing both goals is going to be 49 over 64. All right, we're going to continue to look at tree diagrams. We've got 2 more examples to go, and these ones both involve dependent events, and we're going to look a little bit at some percentages, because percentages often cause a little bit of difficulty. So example 4 and 5 are both going to be dependent examples. All right, so example number 4 says that there's 2 machines, A1 and A2, and they both produce all of the glass bottles made in a factory. The percentages of broken bottles produced by these machines are 5% and 8% respectively. Machine A produces, machine A1 produces 60% of the output, and it says that we want to look at our probabilities here. So there's a suggested strategy. First of all, you want to introduce your symbols to represent the information. We've got 2 machines, A1 and A2, and we have some probabilities there. Once we know what machines we're working with, then we can set up our probabilities. And once we have all of the probabilities laid out, then we can set up our tree diagram. Now again, if you notice here, it says the percentages of broken bottles produced by the machines are 5% and 8% respectively. So 5% for A1 and 8% for A2. So we're going to have to consider some conditional probabilities here. We're going to be looking at the probability that a bottle is broken given that it comes from machine A, or the probability that a bottle is broken given that it comes from machine A2. And so we're going to look at those here right away. So first of all, we set up our symbols. So A1 is going to represent the bottle is from machine A1, and A2 is going to represent that the bottle comes from A2, and B is going to represent that the bottle is broken. So the probability of coming from machine A1, well, we're told that machine A1 produces about 60% of the output. So the probability of coming from machine A1, I'm going to use decimals, is 0.6. And if there's a 60% chance of coming from A1, that means there's a 40% chance of coming from machine A2. Now, we have a probability here of 0.05. Well, that represents our 5%, and it says the percentages of broken bottles produced by these machines are 5%. So the probability that a bottle is broken, given that it comes from the first machine, is 5%. And the probability that a bottle is broken, given that it comes from the second machine, is 8%. So again, these are conditional probabilities. So we're going to take a look at our chart here. The probability of coming from the first machine is 60%. So that means the probability of coming from the second machine is 40%. The probability that a bottle is broken, given that it comes from machine A, is 5%, so 0.05. And so if there's a 5% chance of being broken, that means there's a 95% chance of not being broken, given that it came from machine A. Now for machine B here, we were looking at the probability of a broken bottle given that it comes from the second machine. This is 0.08. And the probability that a bottle is broken given, probability that it's not broken, given that it comes from machine A2, is 0.92. So the probability that it's not broken. So I'll write out our probabilities here. The probability of coming from machine A1 and being broken, the probability of coming from machine A1 and not being broken, the probability of coming from A2 and being broken, and then there's the probability of A2 and not broken. So for the first one here, we've got the probability of A1 times the probability of B given A, and so that's going to be 0.6 times 0.05, which is 0.03. Now the probability of A1 times not broken, normally I'd write out this piece here, but just to save space, I'll just explain it. But this would be the probability of A times the probability of not B given A. So we're going to have 0.6 times 0.95, which equals 0.57. Now for the next one here, the probability of coming from machine A2 and being broken is going to be the probability of coming from machine A2 times the probability that it's broken given that it came from A2. So 0.4 times 0.08 equals 0.032. And the last scenario, the probability that the bottle comes from machine A2 and it's not broken would be the probability of A2 times the probability of not broken given A2. So 0.4 times 0.92, and that gives me 0.368. Now, sometimes there is some rounding involved, so you won't always get these numbers to add up exactly to 1. But if you keep your numbers exact in your calculator, these probabilities should always add up to 1. All right, so we're going to use that diagram to answer some questions. So the first question says, if a bottle is chosen at random, determine the probability that the bottle is a broken bottle produced by machine A1. So the probability that it's a broken bottle and it comes from machine A1 is going to be 0.03. So we're looking for the probability of A1 and it's broken is 0.03. Now for the next question, it says, which of the final outcomes in the diagram relate to the event a bottle is not broken? Well, we have a bottle not being broken here, and we have a bottle not being broken here. So we're looking at the probability of A1 and not B, or we're looking at the probability of A2 and not broken. And the last question here, it says, if a bottle is chosen at random, determine the probability that the bottle is not broken. So the probability that the bottle is not broken is going to be this one here, so 0.03 plus 0.032. Not broken. Oh, sorry, I circled the wrong ones there. I was having a moment. All right, let's try that again. Not broken. I just circled the ones that are broken. All right, so we want the probability that they're not broken. So 0.57 and 0.368. So not broken. All right, so the probability that they're not broken, we're going to have 0.57 plus 0.368. Gives me 0.938. All right, we're going to look at one more example, and I haven't seen a lot of these on diploma exams. However, we do see some questions that involve percentages, and I want to make sure you have a good understanding of these, because often some of the most difficult questions is when we talk about something increasing by a percent or decreasing by a percent. So as we go through this, if you need to review and back up the video a couple times, that's totally okay. Understand that this is one that usually causes some challenges, and so I'll try to talk through it as best that I can. So example number 5 says, as part of an experiment in the learning process, a mouse is put into a maze and rewarded with food every time that it turns right. So here's the case. If the mouse turns right, the probability that it turns right the next time increases by 20%. So the mouse turns right, they get some cheese, so that means they're going to turn right again 20% more of the time. Now, if the mouse turns left, so remember if they turn left, they don't get any reward. If the mouse turns left, the probability that it turns left the next time is decreased by 20% because they're not getting any reward. So we're going to consider all of our scenarios here, and eventually we're going to be drawing a full-on tree diagram. So it says, assume that there's an equal probability that the first turn will be to the left or to the right. So in other words, there's a 50% chance right off the bat they're either going to go right is 0.5 and then left is 0.5 on the first turn. All right, so the first question, it says to let R1 and L1 represent the events. The first turn is to the right and the first turn is to the left. The question said, what is meant by the event R2 given R1? Well, this means that the mouse turns right the second time, given that it turned right on the first try. So we're looking at if there was a P here, we'd be looking at the probability, but we're looking at the event turning right the second time, given that it's already turned right the first time. All right, if I were to write something out like this, left 2 given R1, this would mean the event where the mouse turns left the second time, given that it turned right the first time. All right, so these are just some examples. All right, so let's write out some of these probabilities. So the first one says to figure out the probability, and then we're being asked to use decimals, the probability that the first turn is to the right. Well, we were already told earlier on that there's a 50-50 shot of turning right the first time. So the probability of turning right the first time is 0.5, meaning the probability of turning left the first time is also 0.5. The next question says the probability that the second turn is to the right, given that the first turn is to the right. So the probability of R2 given R1. Now these ones are a little bit trickier. We know that if the mouse turns right the first time, the likelihood that they're going to turn right the second time is 20% more. So the probability of turning right given the first right is going to be the 50% chance plus 20% of that 50%. Now remember, of in math means multiply. So this is going to be 0.5 plus 0.2 times 0.5. So 0.5 plus 0.1. There is a 60% chance that the mouse will turn right the second time, given it turned right the first time. And that should make sense because 60% is 20% more than 50%. Now we could have also done this another way, in that we could have just said 0.5 times 1.2. And if on your calculator you went 0.5 times 1.2, you would also get that 0.6. All right, so 0.5 times 1.2 is exactly the same as 0.5 plus 0.2 times 0.5. Right. And so sometimes these can be a little bit confusing. We can think about 20% more. Well, if it's 100%, if it's 100% of the original, then it's just 0.5 times 1, because 100% is just 1. But if it's 20% more, that's 120% of the original, and 120% would be 1.2. So 0.5 times 1.2 is 60%. The method there I use in the blue is the way you would have likely learned it in junior high. All right, let's take a look at the next example here. We're looking at the probability that the second turn is to the left, given that the first turn is to the left. Well, we're told in the question here that if the mouse turns left, the probability that it turns left again is decreased by 20%. So we're looking at the probability of a left turn the second time, given they made a left turn the first time. So we have a 50% chance of turning left the first time, and now we're going to decrease that amount. So we're going to decrease by 20% of 0.5. Well, 0.5 minus 0.2 times 0.5. is 0.5 minus 0.1, which is 0.4. Now again, another way to look at that is to go 0.5 times 0.8. Because if we're reducing by 20%, that means it's now 80% of the original. So 0.5 times 0.8 will also give me 0.4. So whether you use the blue method or the black method, you should still get to the same answer. It's just like if we think about GST. If I want to add GST to a number here, let's say I go and buy a $10 item and I want to add GST, 5% GST, I can go $10 times 0.05, figure out my GST and then add it to the 10, or I can just go 10 times 1.05, so figuring out 105% of the 10. All right, so that's just a little background sort of on percentages. All right, so we're going to set up our tree diagram, and once we have our tree diagram, then we can get the rest of the information that we need. So we start off with our tree diagram. The mouse starts off right here. We got our cute little, I don't know, I can't draw a mouse. There we go. We got our cute little mouse. He starts off at the maze, and he either goes right or he goes left. And then he hits another junction, and he either goes right or he goes left. And he either goes right or he goes left. Now our probabilities is what we're going to fill in between here. So there's a 50% chance that the mouse goes right. There's a 50% chance that the mouse goes left. Now the probability that the mouse goes right again, given it went the right the first time, is 0.6, meaning the probability that it goes left is 0.4. Probability here is 0.6 and probability here is 0.4. And again, those come from above. So if we want to write out our probabilities here, the probability of the mouse going right and right again is 0.5 times 0.6, which is 0.3. The probability of the mouse going right and then left is 0.5 times 0.4 is 0.20. The probability of going left and then going right is 0.5 times 0.6, which is 0.3. And then the last one, the probability that the mouse goes left and then left again is 0.5 times 0.4, which is 0.2. So now we're going to look at our probabilities. What's the probability that both mice go to the right? So the probability of right and right again is 0.3. What's the probability that the mouse goes left twice? So the probability of left 1 and left 2 is 0.2. And the last question says, what's the probability that they go in opposite directions? Well, opposite directions are right here. So that's going to be the probability of right 1 and left 2, or the probability of left 1 and right 2, meaning we're going to add those two amounts together. We get 0.5. All right, so we've gone through and looked at some ways that we can use tables of values, and we can use tree diagrams to determine some probabilities. Anytime we're dealing with independent and dependent events, tree diagrams are super helpful. Whenever you're doing these questions, it's really important that you first figure out what your variables are, identify all of your probabilities, and then set up your tree diagram. As you work through your unit review, you'll find that there are some questions that are directly related to this lesson. So as you're working on your unit review, I would consider coming back and checking out the video or working through the notes. All right, those are quite a few examples for you. Hopefully you don't have too many questions, but if you do, I'm always available in class. Have a great day, and we'll see you soon.